Alright, 2015 exam, question 18. Let's do the heat and thermodynamics part of it. Thank you, Darren. How much heat is required to change a 0.8 kilogram ice block at minus 40 degrees C to steam at 100 degrees C? Well, most of the energy is going to be in changing it from water to steam. So I'm just going to start with that calculation before I worry about anything else. So let's go to the data. 2.26 by 10 to the 6 joules per kilogram. Okay, so 2.26 by 10 to the 6 joules per kilogram times how much? 0.8 equals 2.26 exponent 6 times 0.8 equals, so they're 1.8 megajoules. That's how much we need to turn it from water to steam. Okay, let's find out how much do we need, say, to how much do we need to melt it. Okay, so melting 3.34 by 10 to the 5th. Okay, 3.34 by 10 to the 5th times 0.8 equals, okay, 3.34 by 10 to the 5th times 0.8 equals 200 times 0.8, sorry, times 0.1 equals, okay, that's 0.267 megajoules. So okay, let's add that to the 1.8 we've already got, and we get, so the total so far is 2.067 megajoules. Right, okay, so by boiling it all and melting it all, we've got up over that. We're not quite up to that, we're a long way from that. It's going to be that, because the other bit, raising the temperature, is not big. It's not big, don't worry about it. I could be wrong. Hey, let's just pretend it's the exam, I'm in a hurry, and yes, I can do it properly if I want to. Okay, now we have an iron rod, 0.25 meter long, there it is, 16 centimeters in diameter. Okay, important. It's placed in ice water and the other in boiling water, and the rod is well insulated, so no heat is lost from the sides. So in other words, heat will be flow from here through there into there. Thermal conductivity is given by that, and right. So in steady state, heat flow is reached. How much ice melts in 1 second? Okay, so how much heat flows, right? So we've got a certain amount of heat. The heat flow, it's going to be, it'll go up with the conductivity, so 80.4 is there. It'll be proportional to the area. Okay, so the area is equal to pi r squared, which is pi times 8 by 10 to the minus 2 squared, which is equal to, so here, pi times 0.08 squared equals 0.02, or 0.02, so 1 blah 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 times, okay, so it's the thermal conductivity times the area. Now obviously the longer it is, the less, so we're going to have to divide by 0.25, the length. Okay, and obviously it's going to be proportional to the temperature difference, so we're going to have to times by 100. That basically should be it. Okay, so let's just do that calculation. So times that by 80.4 times 100 and divide by 0.25. and we're going to get 647 roughly joules per second. Okay. Okay. Now, how much ice does that melt in a second? Okay. Well, we looked it up before. So to melt a kilogram of ice takes 2.26 times 10 to the 6 joules. That will melt a kilogram of ice. If we change that to a 3 there, that'll melt a gram of ice. So 2,260 joules will melt 1 gram of ice. And so what we'll get is 647 over 2260, and that'll be grams. Okay, let's try it. 647 divide 2260 equals 0.28 grams in a second. Ah, I've used the wrong number. I'm talking about melting. Melting. There you go, John. Melting 3.34 by 10 to the 5th. Okay, so again, if we convert that to 10 squared, that'll give us the number of grams, the amount of heat needed. 334 joules will do 1 gram. So therefore 647 divided by 334 is about 1.93 blah 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 grams per second, so close to 1.9 grams. The two significant figures, it is 1.9 grams. So that seems reasonable. Okay, now 200 moles of an ideal gas go from state A to B as shown in the PV diagram below. Which of the following processes is consistent with the graph? Okay. Well, we've always got PV equals nRT, okay? And so if we look at point A, we've got pressure 5 by 10 to the 5th times volume 1 is equal to N, 200 moles, times R, 8.314 times 8.314, okay, times temperature. So solving for temperature, we will go, do I really want to do that? Anyway, who knows. So temperature is 5, exponent 5, divide brackets 200 times 8.314, close brackets equals, so T at point A is equal to 300 Kelvin. Okay, so it can't be isothermal expansion at 500 Kelvin because temperature at A is 300 Kelvin. What about the temperature at B? This appears to be a relatively easy thing to do, so rearranging that, PV over nR is equal, so at B, our pressure is now 0.5 by 10 to the 5th times V, which is now 4 over N, which is 200, and R, which stays the same as well, 8.314. So let's have a look. 0.5 times, start again, John, 0.5 exponent 5 times 4 equals, divide, oh, how annoying, try that again, 0.5 exponent 4 times 4 equals, no, try again. We're just not going to get there, are we? 0.5 exponent 5 times 4 equals, divide brackets, 200 times 8.314, close brackets, equals 120. Okay, so it certainly isn't isothermal expansion. Now, isochoric isochoric means equal volume. So in other words, if you expand, and it doesn't even make sense. Isochoric, equal volume expansion. An expansion means you change volume, and it's at 200, so it's not at 200. Okay, so they're all eliminated. So okay, so we're left with its adiabatic expansion with one of these values of gamma. And we know for adiabatic that PV to the gamma is a constant. So at point A, PV to the gamma is equal to 5 by 10 to the 5th times 1 to the anything, 1 to the, it doesn't matter which one it is, it'll be the same. So it's going to be 5 by 10 to the 5th. So at point B, PV to the 1.1 is equal to 0.5 by 10 to the 5th times 4 to the 1.1, which is equal to 0.5 exponent 5 times 4 raised to the power 1.1 equals 229,739, and that's not the same as that, but we've got to check to make sure. So we think it's not that, but we've got to check that at B, PV to the 1.67 is 0.5 times 10 to the 5th times 4 to the 1.67, so that's 0.5 exponent 5 times 4 exponent 1.67, no, delete, times 4 y to the x, 1.67 equals, and that's 506,000, so basically 5 by 10 to the 5th. So yes, so D is the most consistent. That's why you hate Darren's questions, because they're hard. Right. Let's look at the next question. A gas undergoes an isothermal expansion. What is the sign of the work done on the gas and the heat absorbed by the gas? So when a gas expands, if you want to make it isothermal, it does work as it expands. So therefore, you must pump heat into it, right? Because otherwise it would lose temperature by losing internal energy because it's doing work. So what is the sign of the work done on the gas, right? The work done by the gas is positive, so the work done on the gas must be negative. Okay, so this one, no. Zero heat absorbed, no. Okay, and it must in fact be positive heat absorbed, because it does work, and the gas does work, so it must absorb heat, otherwise it would lose temperature. So it's B. B is good. I get the feeling we've now done Darren's easy question. Right. Now, a monatomic ideal gas undergoes a Carnot cycle through states A, B, C, D and back to A as follows. State A, pressure's 5,000 pascals. Ooh, okay, so that's there. That one's got to be A. And volume is 1 cubic meter. State B, 2,500 pascals and volume's 2. So that's B. State C, well, that's got to be the next one. Has to be there. 790 and volume's 4. Looks good. And state D, 1.6 by 10 cubed, 1602 there, and then back to A. So it goes down this path. Okay. Now, looking at the PV diagram above, decide which of the following best represents the work done by the system. So here it's doing work, and the work it does is equal to the area under that curve. And here, coming back, it's having work done on it, and the work done on it is represented by the area under that curve. So the difference is this area here, and that's the net work that's done by the system. So, you've got to decide how big that is. Well, at its biggest, it's the difference between those two, which is between 1600 and 2500. So at its biggest, it's 900 pascals, and the change in volume is 3. So that's approximately equal to 2700 joules, or 2.7 kilojoules. Now it must be smaller than that, because in fact, as I said, that's the biggest, and it's smaller most of the way. So looking at the answers, 15 joules, too small, 4 megajoules, too big, negative, wrong, 2 joules, too small, there. 2.7, half that, beautiful. Can't argue, it's got to be good. That wasn't the end of the easy questions from Darren, it was another one. Okay, 4,000 moles of an ideal gas at 400 Kelvin undergoes an adiabatic expansion until the temperature is 300. The initial volume of the gas is 1 cubic meter. What is the change in entropy of the gas? Right, so one of the things to remember about in the sort of processes that we have in thermodynamics, which is the quasi-static processes, the ones that happen slowly, smoothly, when equilibrium is maintained the whole time, is that the change in entropy at any time is just the change in heat divided by the temperature. Okay? And the second thing to note is the definition of adiabatic is the amount of heat going in or out, dQ, is equal to 0. So that makes this question even easier. Oh, beautiful. Right. Getting there, slowly but steadily. In a closed but uninsulated container, 500 grams of water is shaken violently until the temperature raises by 3 degrees. The mechanical work used in the process is 9 kilojoules. How much heat escapes from the container? So basically, this is saying, look, we did 9 kilojoules of work on this water, and it raised the temperature by 3 degrees C. So that's how much of the work we did which remains as heat in the water. The rest must have escaped. So if we have a look, we can see that specific heat of water is 4184. So the heat is 4184, the specific heat, times half a kilogram times 3, and so 4184 times 0.5 times 3 equals 6.276 kilojoules. Okay, we put in 9 kilojoules, joules. Yeah. We put in 9. This is how much was used to raise the temperature. Well, the rest of what was lost. So take away 9,000, and I get 2.7 kilojoules. How much heat escapes? 2.72 kilojoules. Why is it not minus? Well, minus would imply that heat was added. It escaped, so it's positive there. Alright. Right, the beaker contains 700 grams of water at 15 degrees Celsius, and it's heated to 83. What's the change in entropy of the water? Okay, I'm just going to do look at the formula sheet first, see if they've got something nice. I just want something easy. I'm tired. Let's see. Entropy. No, look, this one's going to work. MC log T2 over T1. This is where your specific heat C is constant. So MC log T2 over T1. Okay. Delta S equals MC logarithm T2 over T1 equals, okay, so M 0.7, C 4184 times log of, now we've got to get this right because these temperatures of course are in Kelvin, so it's 273 plus 83, so that's 356 over 273 plus 15 is 288. Okay, and we'll do this and say 0.7 times 4184 times natural log of brackets 356 divide 288 close brackets equals 620.8, and 621 is pretty close to that, so I'll go with that. Alright, does it make reasonable sense? Well, look, a rough estimate is always going to be that what's the average temperature of 15 and 83? 15 plus 83 equals, divide 2 equals 49 plus 273. A rough estimate is that T is approximately 322 Kelvin. Okay, and so we can say that the change in entropy, roughly speaking, is going to be the heat added, which is going to be 0.7 times 4184 over 0.7 times 4 times the temperature difference, which is 15 times 83 minus 15. 83 minus 15 equals 68. Okay, so let's do that and see it's roughly right. 0.7 times 4184 times 68 gives us the heat added. We divide by 322 the average temperature, and we get 618.5. So close enough. Okay, not exact, but it's good enough. Makes me think we're in the right ballpark. Last heat and thermo question from 2015 exam. Gas tank with a volume of 5 cubic meters has circular end caps 1 meter in diameter. If the gas contains 1,000 moles of nitrogen at 20 degrees C, what is the total force due to the pressure of the gas inside the tank on one of the end caps? Okay, is this hard? I don't think so. Let's go. PV equals nRT. What's the volume? Okay, it's got a volume of 5 cubic meters. Okay, so therefore the pressure is equal to nRT over V, which is equal to N 1,000 moles times R 8.314 times T, which 273 plus 20 over V, which is 5, and this is going to give us a pressure. Right, so pressure 1000 times 8.314 times brackets 273 plus 20 equals, divide 5 equals, so the pressure is going to give us 4.87 by 10 to the 5th pascals. Okay, doesn't want the pressure though. Okay, it wants the force due to the total force due to the pressure on one end of the cap. So force is equal to pressure times area. Okay, so 4.87 by 10 to the 5th times the area, which is pi r squared. So that's 4.87 by 10 to the 5th times pi times the caps are 1 meter in diameter, so the radius is a half a meter. Okay, so that times pi times 0.5 x squared equals 382 2006 blah blah 00, basically 3.83 by 10 to the 5th newtons. That one. Okay, done.